Hi, and welcome to Lecture 11 of Applied Machine Learning. In Lecture 11, we're going to start a new topic called kernels. Kernels is an interesting and important topic, and the motivation behind the idea of kernels is how to make our machine learning algorithms more flexible and more nonlinear. So far, most of the models that we have looked at, both for regression and for classifications, have been linear models. So they were a linear function of the input x. And in this lecture, we're going to look at a new way in which we can make them nonlinear without really increasing their complexity and without really making them more challenging to work with. And this is going to be a general approach that will be applicable to most of the machine learning algorithms that we have seen so far. And in fact, is going to extend beyond supervised learning to unsupervised learning as well. And this is the core idea is going to be that of kernels and the so-called kernel trick. So before I define kernels and the kernel trick, I'm going to start with a little bit of motivation. I'm going to start with a high-level observation about one of the algorithms that we have seen so far, and then I'm going to give you a high-level idea of why the approach of using kernels is interesting and how it can be powerful. So in this video, we are going to start by looking at the high-level motivation behind using kernels. And we're going to start with a really simple algorithm, which was the first algorithm we have seen in this class, which is linear regression. So recall that in linear regression, we assume a model of this form, where the output of the model f of x is some kind of linear combination of the input attributes x, which we can write in a vectorized form as theta transpose x. So theta here are the parameters of the model, and x is our input, and it's a vector of input attributes. In one of our first lectures in which we talked about linear regression, we saw that we can train these models using the mean squared error loss, which is simply the squared difference between the target that we have for our input and the prediction of the model, which is here theta transpose x. So we take the difference of that, we square it, and then we look at the average over the data set. And later on, we also saw that we can regularize this objective, which means that we add a penalty on the weights of theta, and this encourages us to find a solution that both have a small error and whose parameters are numerically small, and that turns out that the solution is going to be better behaved numerically, is going to overfit less, and is going to better generalize to new data. And the algorithm that we have seen, which learns this vector of parameters using an L2 regularized objective, was called ridge regression. This model that I just showed you earlier on the previous slide is fundamentally a linear model. But in one of our earlier lectures, we saw that in principle, we can take any linear model and we can make it nonlinear by defining nonlinear features phi of x. So here, phi can be any kind of feature. It can be either a polynomial feature, or it can be a set of sines and cosines that are derived from x. So phi of x can be highly nonlinear, but it remains linear in theta, which means we can use our standard, we can use all the standard techniques that we have seen in this course to learn theta, and we still in the end have a nonlinear function of x. So I'm going to explore this approach a little bit more in this video. And in order to make it a little bit more, I'm going to start by introducing a little bit of notation to make things more precise. I'm going to introduce this new matrix called phi, which is simply going to be our featurized design matrix. Recall that in one of our earlier videos, we defined the design matrix, which is simply a matrix in which we take all of our inputs x as being the rows of this matrix. So we simply stack all of our input vectors one on top of another into this to form a matrix, and that was called the design matrix. The featurized design matrix is the same, except that instead of stacking together the raw vectors of attributes, we are stacking here the vectors of features. Here, each x is an input with some raw attributes. Now we have featurized it with phi. That is another column vector of dimension p. And now we can simply take each of them to be a row. We take the transpose to make it a row vector. And now we just stack all of these rows one on top of another to form a matrix called the featurized design matrix. And if our phi were attributes instead of features, we would have our design matrix. But now, just to distinguish between attributes and features, I'm going to use this symbol capital phi to denote the featurized version of this matrix, in which the inputs are features instead of the raw attributes. So at the position ij of this matrix, we have the jth feature of the I input point. And we saw in our earlier videos that we can find, given a design matrix, we can use this design matrix to compute a closed form solution for the parameters of a linear regression model using the normal equations. The normal equations were a closed form solution for the theta which minimizes our mean squared error objective. So with a design matrix X, this was our formula. Here, this is we have this term lambda because this is for an L2 regularized mean squared error objective. And given that our features are, given that our inputs are featurized, we can do the same thing except for the featurized matrix. So in other words, I alluded to earlier that if our inputs are described by some kind of highly nonlinear features, we can solve them as if in the same way as we would solve a linear model, as long as it's linear in theta. And specifically what I meant by that is that we would instead solve the following equation, which is simply our normal equation, but now I am computing this in the space of features instead of in the space of attributes. So this will give us a solution for the optimal parameters theta when the inputs are featurized with some features phi. Now I would like to do two things to this algorithm that I'm starting to define, or I would like to apply a transformation to this set of normal equations that we had on our previous slide and that we're familiar with. I'm going to transform them in one little way. In order to do this, I'm going to use the following identity from linear algebra that is sometimes called the push-through matrix identity. And the idea behind the push-through matrix identity is as follows. Suppose we have two matrices U and V. This should say V. Then we can, then the following identity holds. So here I have an inverse of this matrix times U, and it turns out that I can move U to the other side and I can flip the order of V and U, and this will be the same. This is an identity in linear algebra. It is not very important to show the proof, but or for you to fully understand the proof. But the proof is actually really simple if you want to look at it as an exercise. But essentially, in order to convince yourself that this is true, you may start with the following identity, which is actually fairly straightforward. Here, I'm multiplying u. Well, you can convince yourself that this is the same by just multiplying it out on both sides. So we have lambda u plus uvu on both sides. It gives us exactly the same expression. And now consider multiplying both sides by this matrix from the right and this matrix from the left. And as a result, we are going to obtain the following identity. When I mean multiply by this term on the right, here I am simply taking the left-hand side and then I multiply by this matrix from the right, which means that this and this matrix is getting multiplied by its inverse, which means it cancels out. So on the left I have u, on the right I have this inverse that is now multiplying u from the right. Now I do the same thing with this matrix but multiplying it from the left, and you can convince yourself that this gives us the following identity. So given that this is always true for any choice of matrix u and v, I can simply set u to be phi transpose and v equals phi, and I can apply this identity to my set of normal equations to obtain a different form for the normal equations, which is called the dual form, sometimes referred to as the dual form. In other words, here, this form, you can easily check that this is equivalent to this side of the equation with the following choice for u and v. And then what I have here is simply the right-hand side of the equation with the same choice of u and v. So here, this is applying a different identity, but it gives us a different formula for the optimal weights theta. One observation that we might want to quickly make about how these forms compare to each other is that here we are taking so phi is going to be an n by p matrix. It's going to be an n by p matrix, and therefore this is going to be p by n. We are forming a p by p matrix, or d if we call the dimensionality of the features d or p. Then here we're going to be doing an inverse of a d by d matrix, which takes d cubed time. But here this product is going to have dimension because now we flip the way the matrix are multiplied. This is going to be a squared matrix of size n by n, where n is our number of data points. And taking the inverse of this matrix is going to take n cubed time. So actually, this is going to be a little bit faster if d is greater than n, because this expensive cubic operation is going to be in a number that's smaller. So if we have a very large number of features, then this might be preferable. It will be preferable if our number of features is greater than the number of data points. This is just one distinction between these two equations. It is not terribly important, but you might want to convince yourself that it's true in order to better understand these two formulas. But now let's make another observation that is even more important. A very important observation that I'm making on the slide is the following. Here again, this is our dual form for the normal equations, and this here on this set of the result of this set of multiplications and inversions and additions, you should convince yourself that this is a vector. It's going to be a vector of dimension n. Here, this is a square matrix of dimension n by n. I take its inverse. That gives me an n by n matrix. Y is a vector of size, it's a column vector of size n. I multiply an n by n matrix by a vector, a column vector of length n. This will give me, this entire set of operations will give me another vector also of dimension n, which I'm going to call alpha. And now we can see that our set of parameters theta is nothing but the product of the feature matrix phi with this new vector alpha that I defined. And in fact, we can write it out in a more explicit form like this. So theta is going to be the product of phi transpose times the vector alpha. And because each column in phi transpose is the featurization of the ith example, right? The ith column of phi transpose is simply the ith featurized example. When we multiply this by a vector alpha, we're simply summing the columns with these weights alpha I. And now the form for theta is going to be as follows. And this is a really important form. What this is saying is that the optimal set of parameters theta for our ridge regression model with features phi is a combination of, it's a linear combination of the n featurized training points. So the parameters theta are a linear combination of the features that are measured over, where the features are computed over the training points xi. This is a very important observation. Here again, just to convince yourself that this is true. Again, this is our form for alpha, and let's say that L is an n by n matrix. Well, let's call this n by n matrix. That's the result of these operations. Let's call this n, and then alpha I is going to have this particular form, and this is going to be a linear weighting of all the features. This is a very crucial observation that's going to be at the heart of many algorithms that involves kernels. Why is that interesting? It's interesting because let's say that now let's suppose that I would like to make a new prediction for a new input x prime. Because we have a linear model, and just by the definition of our linear model, the output of the linear model at x prime is going to be simply phi of x prime dot product with theta. This is just applying the definition of my linear model. And now, given that I know that theta is a linear combination of the weights phi, I can just apply the definition that I had earlier to obtain the following expression. So here I did nothing but plug in my definition for the vector theta, which is sum of alpha I times phi xi, and now I can take this dot product inside the sum, which gives me the following expression. Let's now look a little bit more carefully what this is. It's saying that it says that the model predictions at the optimal set of weights theta is nothing but a linear combination of, it's nothing but an average of the dot product of the features phi times the features of each training example, and these are weighted by the set of weights alpha. And well, first of all, there are many intuitive interpretations about this that you could make, and we're going to dive into this a little bit deeper. But the key observation here is that if I know the alpha I, and if I can compute these dot products efficiently, I can obtain a prediction without ever actually needing the vector phi itself. In other words, the features themselves are not directly used in the equation. Only their dot product is used. So if I can somehow compute the dot product without really requiring the features, then I can still use this algorithm. And if it happens that I can compute the dot product very efficiently, more efficiently than computing the actual, than what it would take to compute the actual features, then I can significantly accelerate the at least inference in this kind of model. And this observation will actually, this approach, it will actually be something that we can do, and this idea will be something that we're going to refer to shortly as the kernel trick. This trick is even more powerful than what it's actually more interesting and more general than what I said earlier. It's more general because we can avoid, we don't need the features themselves, but their dot products, not only for making predictions, but also for learning theta. So to convince yourselves, again, let's consider our matrix, our vectorized feature matrix phi, in which row I is simply the ith featurized input, and then we can consider the matrix phi transpose, which is simply the matrix of all the dot products between all the phi of xi that we have. So K is an n by n matrix, and the ith jth entry is the dot product of features of the ith theta point with the jth theta point. And by our earlier definition of alpha, if we plug in this K times phi transpose into our definition of the norm of alpha, which we derived from the normal equations, then we have the following form. And in order to compute this vector of alpha, we again do not need the features themselves. Here, the only way in which these features find themselves are via the matrix K. And so if we can have K without the features, if we can compute K efficiently, then we can use this formula to efficiently compute predictions at new sets of features x prime. In other words, given that I have a new input x prime, I can do the following. I can first compute this alpha, which again only requires me to know the dot products. It doesn't require me to know what the features are. And then I can use it to make predictions using the formula that I had in my earlier slides. This is, again, an instance of something that we're going to call shortly a kernel trick, or the kernel trick. And if we can compute these features effectively, as we're going to be, the dot products of these features, if we can compute that quickly, and I'm going to show you soon how we can do this, then it's going to significantly accelerate the speed at which we can perform machine learning with nonlinear features. So again, this slide summarizes what I said earlier. Here, what I have described is an early version of something that is going to be called the kernel trick. And now in the next video, I'm going to show you how we can exploit this kernel trick, how we can make it even more precise.